on transmission expansion studies. And I'd like to introduce Juliet Homer from the Pacific Northwest National Laboratory, who is going to moderate this session.
Thank you, Debbie. Hello, everyone. So welcome to this session on transmission expansion studies. I'm Juliet Homer from Pacific Northwest National Laboratory, and we are excited you're with us today, and we've got a great panel here. Okay, so I'm going to start. This panel is actually going to be addressing some work that we have all done on the National Transmission Planning Study, which was funded by U.S. Department of Energy's Grid Deployment Office. So we want to thank them for that. And it was been a joint effort between PNNL and NREL. So I'm going to start with just a little bit of background about the study, and then we're going to turn it over to, I'm going to move over here. Turn it over to David Palchak, Manager and Research Engineer at NREL, who's going to present on resource adequacy and HOT paths, or high opportunity transmission paths. And then we'll turn it over to Amy Rose from NREL, and she will talk about the economic analysis, benefit cost of portfolios, and regional insights. Then we'll hear from Jarrad Wright, a senior researcher at NREL, and he'll talk about the zonal-to-nodal and transmission plans and production cost modeling. And then system security and AC power flow will be the last presentation in this panel, and that'll be given by Nader, Samaan, Chief Engineer and Team Lead at PNNL. And we'd love to have robust discussion. So as in the last panel, as we go along, please make notes of questions that you have, and we want to hold those questions to the end, but we're going to have some good time for some discussion. And as I said, this is results from the National Transmission Planning Study that we've been working on over the last about 2 years. So the objectives of the National Transmission Planning Study were to identify interregional and national strategies to accelerate cost-effective decarbonization while maintaining system reliability. We were also looking to inform national or regional and interregional transmission planning, and particularly having engaged stakeholders in dialogue. And then finally, we hope that the results of this National Transmission Planning Study will help prioritize future DOE funding for transmission and infrastructure support. So I want to thank all of you out here who have been participating as one of maybe our technical review committee members. We had a really robust stakeholder engagement process through this project, including tribal engagement. We've had public webinars, we worked with existing groups, and we had a technical review committee, or a TRC, that was comprised of a government subcommittee, a modeling subcommittee, and a land use and environmental exclusion subcommittee. So we really appreciate all the feedback that we received throughout the course of this study, and we were able to adapt and our approaches and assumptions based on feedback. So thank you to those of you who've participated. So today you're going to hear about the results of the transmission expansion planning and modeling. But we have some companion reports that I want to point to before we get into the bulk of the material here. First, is this Interregional Renewable Energy Zones report that was just released, I think, 2 weeks ago and is now available. And it identifies potential IRES zones, just like kind of after the Texas CREZ model we heard about on the last panel. And it points to potential transmission lines that would bring the lowest cost renewable resources to load centers. So this isn't the full results of our study, but I think this is an example of the types of things that can be done with the results of the study that we're embarking on here. And it's maybe an example of places that states can start to look at different renewable energy zones that would be part of their state. So if you're interested in this, there's a link, but you can also Google it. It's hot off the presses. Another companion report that's going to be released in May is one called Regulatory Pathways to Interregional Transmission, a Landscape Assessment. And in this report, we summarize the current transmission planning and development landscape in the United States. It's a patchwork, and this report's really kind of tailored for states and folks who may not know all the details of transmission planning and development. In this report, we assess regulatory obstacles to interregional transmission. We heard about some of those in the last panel. We survey potential solutions that have been proposed to interregional transmission challenges, and then we share some examples from other countries. A third companion report is called Mending Seams, Barriers and Solutions to Increase the System Value of Interregional Transmission. And this report is going to be released in June timeframe, and it explores options for increasing the efficiency and utilization of existing interregional transmission assets. And then we're also releasing a Western interconnection baseline study that digs deep into the Western interconnection. So those are to come, but now we're going to dig into the bulk of the study today, and we're going to start out with David Palchak. But before we do, one more slide I forgot about our timeline. And all this to say that we are going to be wrapping up, and the final report will probably be released in late summer, and we'll have a final public webinar. So with that, I will turn over to David Palchak.
Thank you, Juliet. I'm going to step off the stage here to try and address the audience. Thanks, Juliet. So I'm going to be talking about some of the results of the study. So as Juliet said, these aren't necessarily public, but we're happy to share them. And as she showed, we've been working with stakeholders throughout that. So happy for any feedback that we have about this. I'm going to focus a little bit on one of the primary outcomes, which is a high opportunity transmission analysis. So I'm presenting on this, but there's a lot of others, True My, Ann Hamilton, Patrick Brown, who did most of the work for this presentation. So, and there's a very large team that works on this. So just dig in here. So just to put this in perspective of other things going on in the country. So this is not the Department of Energy needs study. So you heard about that a bit in the last panel if you were there. This is not that. We get confused with that quite a bit. So I just wanted to put that up front. Everyone should go read that. It's very interesting, but this is a separate product. There's also several other related lab-led studies, the Atlantic Offshore Wind Study and the Western Offshore Wind Study. Atlantic was recently published. We do have coordination with them. We work with PNNL on those studies as well. So certainly trying to coordinate where we can in some of our offshore assumptions. Those are some other important activities. And some other relevant but totally separate activities that I just wanted to point out in case there was confusion. It's the NITSEs that was brought up in the last panel as well. So totally separate. We really don't have any connection with that. We are funded by the same office, but that's a different process. And I think that was talked through enough in the last session. Also, the NERC Interregional Transfer Capability Study, certainly very interesting work going on there, but separate, but certainly a couple at the national scale. And this is not a comprehensive list, but just wanted to kind of put that in perspective. Okay, so this is getting in the National Transmission Planning Study now. So we use a multi-model framework to better understand and meet the objectives that Juliet talked about, but ultimately to rule in opportunities for transmission in the US. Over here in the blue box, so this kind of separates our study into the different types of models we're using. So over in the blue box is our zonal modeling. We do things like capacity expansion, economics, and resource adequacy over in that box. So we call that zonal. And we look at bigger picture. So we have 134 zones across the country and trying to understand from a big picture, a little less granularity, what is needed in terms of resources and how can transmission be built between those zones. So when Amy and I talk today, we're going to be in those blue boxes. Jarrod's going to talk a little bit about this gray box, which should be bigger. It's a big deal in terms of how much time and effort it takes in this study and how important it is. But we translate those into actually transmission network solutions. And then we go into our nodal analysis. So looking at things like production cost at a nodal level, doing power flow and additional stress tests. So this middle one is kind of the transmission planning phase. Okay, so Amy and I are in zonal. Jarrad and Nader will be talking more in the green boxes. And so when we work in the zonal world, we're allowed to look at or able to look at several potential futures. So we run a lot of different scenarios of the future, and I'll walk through our scenarios a little bit in a minute here. But for this study, we were able to do about 100 different scenarios out to 2050. But when we get into the nodal world, that's very difficult to translate these. We're doing about 3, at least at this phase in the study, and that's for a single year in 2035. Okay, so just to hopefully set up the next presenters a little bit, since we're all in the same study here. So I'm going to be talking about the many opportunities for interregional transmission. Again, in the zonal world, Amy's going to talk about the benefits, a little bit about the costs. Jarrad will then talk about some of the network solutions, how resources can balance in these very detailed network models. And then Nader will talk about reliability and how it can be maintained in these very transformative systems. Okay, so I need to give a little bit of background about the scenarios before I jump into results. So our scenario framework, so as a transmission study, we have several types of transmission paradigms as kind of one of the important kind of layers of our scenario matrix. So I'm going to refer to a limited scenario. That means that we're not allowed to build interregional transmission. So those black lines, it's kind of hard to see. You cannot build transmission across those lines. You can build AC within those regions. But we also put a limit on the amount of AC, and you'll see that in some of the results. And that limit is based on essentially historical averages. We have 3 accelerated frameworks. An AC scenario where we allow expansion across the interconnection. So you can see the eastern, the western, Texas, all those black lines are removed. You can build as much as you want within those interconnections, just in AC and existing DC. We have point-to-point, so this is long distance HVDC. So this map here is a little bit confusing. This is essentially what the model can see as options. That's not what ultimately gets built, as you'll see, but the model can build these HVDC lines if it wants. And this is a least cost planning model, I should say. And then multi-terminal, so expansion across the country using different assumptions for cost in multi-terminal HVDC, and usually just with neighboring regions, you're not seeing those really long distance HVDC. So these are the 4 paradigms that we're going to talk through a little bit, usually comparing things back to the limited. Additionally, we also look at different demand. So we have 3 demand growth trajectories. I'm only going to talk about the mid today for the results, and that's the one we kind of focus on more. We call it our central scenario because it's in the middle, no really other reason. And we also have 3 emissions targets. So we have a current policy, so this includes Inflation Reduction Act and other state policies since that were in the books up to June of last year. We also have a 90% CO2 reduction by 2035 and 100%. So I'll mostly just talk about the mid and the 90% reduction scenarios to get me through this in a reasonable amount of time. Okay, so getting into the results. So this is the 90%, again, mid demand. So we're seeing rapid and significant growth. So people are used to these sorts of trajectories, I think, at this point. A couple things to note. So obviously we have our 4 transmission scenarios here. The limited here is basically maxing out what we're allowing it to do. So it's building everything it can given the kind of single historical average number that we gave it. The accelerated framework's obviously building a lot, 2.5 to about 3.5 times what we see in 2020. And the HVDC scenarios, again, building even more than the AC scenario. So when we let it see HVDC, we're still allowing AC builds wherever it wants. But certainly the HVDC coming at different costs and assumptions, and essentially the model likes that, and it's building it. So a little more granularity on the results here. So the transmission capacity here, what we see in this chart is the different types kind of stacked up. And with the limited, what you can see is this, the gray is the spur and reinforcement. So this is essentially, you think of it as local interconnection costs. And this is, again, kind of maxing out what we allow it to do. And there's kind of some interesting takeaways from that, in that it's not building really anything else in terms of transmission when we limit it, but it's building out as much as it can just in spur and reinforcement. And kind of the other takeaways, when you look at the accelerated frameworks, the spur and reinforcement increases quite a bit. And a lot of that comes from the fact that these trajectories are driven a lot by the wind and solar deployment. And so we need a lot of spur and reinforcement for that. And so all types of transmission are being built. And certainly when we allow it to see the interregional, it's building that quite a bit. The other thing is that transmission is added essentially across the country. So this is just our 90% scenario again. So in the AC scenario, the point-to-point and the multi-terminal, you see some trends there where a lot of the middle of the country is building a lot of transmission, but we do see it built in all areas of the country. And so that's an important takeaway, that it is important across the country. And the other thing I wanted to point out is that, so in AC scenarios, we're not building HVDC across the seams or AC, because we're not looking at that question. But when we do allow it to build across the seams, it builds quite a bit. So you see in the point-to-point, right here is the interconnection seam, and across Texas, there's a lot built across those seams in these HVDC scenarios. Okay, so shifting back to our scenario framework. So we looked at all these transmission paradigms with the demand and the emissions. We also looked at 15 sensitivities, so I'm not going to go into these. Essentially kind of changing the costs of things, changing the availability of technologies that maybe we're not quite sure about, to try and understand all these different potential futures. So I'm just going to show a chart next with all of these different sensitivities on them. I wouldn't worry about any single one because we don't have time. But just to show that there are trends across all of these sensitivities that are pretty obvious. So if you look up at our core, that's the one we saw before. And across all of these, you're seeing quite a bit of variability, but you do see some trends. The middle of the country still builds a lot of transmission, but with different assumptions, you're going to see very different realities. The kind of interesting ones are where we don't allow some of these nascent technologies to build in the transmission, and oftentimes it gets very, very big in those scenarios. Okay, so I think I'm going to make it. So we also wanted to look across, we had a lot of scenarios, and we tried to apply a scenario-based framework to understand, where are the robust solutions across a lot of these. And so we did sort of a statistical analysis to look at high opportunity transmission. We're calling it the hot paths. So we think we're pretty clever. So the results of this section are going to look a little different than the last maps I showed. So I was showing a lot of 2050 results in those last ones. These are all based on 2035. Okay. So as I just said, we're using those results across a large collection of our scenarios. And we're looking for robustness. And I think I covered most of that. And again, focusing on 2035 ultimately because we want this to be valuable to those that are out there in the industry. So focusing on some of these near-term kind of results for this. So I'll be talking about the FERC 1000 sub-regions or whatever we want to call them, but this is the map you could think of. So dividing up some of the bigger regions into their sub-regions and trying to give some results across all of these black lines essentially, which you'll see in the next map. Okay, so when we approach this, we essentially would take a single AC paradigm and we would lay out all the, an AC and a policy and the demand scenario. We would lay out all the sensitivities for these. And so this is the 16 sensitivities for this specific scenario framework thing. Okay, so we have the 16 different sensitivities here, and we're essentially trying to figure out what's a semi-conservative estimate across all of those sensitivities. So this yellow line represents the 25th percentile, and those are the numbers I'll show in the next maps. So semi-conservative estimate of what we saw across all the sensitivities, and I think that's it. It's worth noting that these are not really non-random sensitivities. We were looking for specific questions about costs, about availability of technology. So this isn't perfect, but this is kind of showing some robustness given that most of the sensitivities are showing at least the numbers I'll show or higher. Okay, a lot of caveats, and the only one I'm really going to pay attention to here is that the increased transfer capacities, these can be achieved from a lot of different things. When you look at our maps, you might think that all means new builds or it all means greenfield additions, and that's not really the case. Even within our nodal modeling, we're finding some rights of way where we can double the capacity of that. So this could come from a lot of different things, including grid enhancing technologies. We're just trying to send the message about the total capacity that might be needed in these scenarios. So the way you get there is really not the biggest concern for us. We do have to make assumptions about our modeling that leads us to some of these numbers, but ultimately we know there's a lot of work to figure out how you would actually get these capacities. Okay, so first looking at the AC, again, the disclaimer. And so these are the results across all the sensitivities, again, kind of a conservative estimate. And so I put some numbers up here just to give context. So if you look at MISO Central to PJM East, there's currently about 28 gigawatts of capacity between that region. And by 2035, our models are showing 12 or more in most of our scenarios. again, out in the west, currently 2.5 between Northern Grid South and West Connect North, imagining another 6 by 2035. So semi-conservative estimates on these. One thing to point out, most regions see a lot of growth, even in some of our more conservative scenarios. So it's happening all over the country. There are opportunities all over the country. So that's kind of an important point. And again, this is the AC scenario. You're not seeing anything on the seams yet. So moving on to our HVDC scenarios, and I'll have those maps up at the end if you want to look at them more. So this is our point-to-point. So you start to see some obvious trends here. So some of those bigger capacities that we saw in the AC. So if you look again at MISO Central, PJM East, no longer 12 between that region interconnection necessarily, but there is still a lot going into PJM, and some of that's met with longer distance HVDC. Again, crossing seams. So we see a lot built along the eastern-western interconnection seam, as well as ERCOT and the interconnections. So a lot happening here. Is kind of a very different view of things with this long distance HVDC that we don't have in this country right now. So, and then finally, the multi-terminal gets kind of crazy. So you can see, we were talking about 12 gigawatts there. We're essentially doubling that by 2035 in our multi-terminal scenario. And again, some really big numbers, tens of gigawatts. In a lot of the kind of feeding the wind belt back to load centers. So as I said, there are certainly opportunities around the country for different regions. I think there's an opportunity for essentially every region on every map to think about interregional transmission. And the other point is that there's a lot of sensitivities where the numbers are a lot bigger. So if you think back to our graph of the bar charts with all the sensitivities, some of those are pretty flat, where some of these numbers might represent what you see in all the sensitivities. Others are very steep, where if you don't have CCS, if you don't have hydrogen, they get quite steep at one end. So it's worth pointing out. But again, this is certainly a lot of interesting opportunities for interregional transmission that stood up to a lot of kind of scrutiny in terms of our scenario design. I made it.
Right. Thank you, David. So I think David set us up nicely to talk about the rest of the study and all the downstream modeling that was done based on those main scenario frameworks. I feel like I'm too short for this. No, it's okay. So I'm Amy Rose. I'm a senior researcher at NREL, and I've been working alongside a big team of folks at NREL and PNNL to look at the economic side of some of these modeling results. And we really focused on 3 main questions. The first is, what are the system-wide benefits of transmission? What are the different types of value that these different transmission frameworks are providing? And how is that value changing over time out to 2050? The second question is, who's benefiting from transmission? And this was something that came up a lot in the previous panel about cost allocation and how benefits are being disaggregated. So we also looked at not just quantifying benefits, but then regionally disaggregating those to understand how different regions were benefiting, and again, how those trends were changing over time. And then finally, can we actually realize those benefits under current rules and operating practices that we have today? Could we actually get that same level of benefits? We looked at that, and that's the paper that Juliet mentioned earlier. That'll be a companion report, but we'll touch on that briefly today. So first, before talking about any results, when we talk about savings and benefits from transmission, we are comparing our AC, our point-to-point, and our multi-terminal scenarios against that limited reference case, holding all other assumptions equal. And we selected a range of different types of benefits for evaluation, including different types of avoided capital cost, avoided operating cost, and reduced costs of meeting reliability requirements. It's worth noting that some of these things in these bullets are not mutually exclusive. So we didn't necessarily individually calculate the benefits of each of these things separately, but we looked kind of as a whole, how are system costs changing to capture kind of at a portfolio level, what are the different benefits that these transmission frameworks are providing. Also worth noting that there are many other benefits that are in literature or that actual regions are quantifying that we didn't capture here, like improved resiliency, reduced loss of load probability, even more downstream, improved air quality and health outcomes. So there's certainly other things that could be included. But at a very high level, we found that across all of our sensitivities, the accelerated transmission frameworks, AC, point-to-point, multi-terminal frameworks, reduce system costs by hundreds of billions of dollars. So this chart on the left shows the net present value of system cost for each of our main frameworks, with the bold colored line being our core mid-demand 90% by 2035 scenario, and then all of the gray lines being different sensitivities. And the middle chart shows the savings. So that's the delta between, for example, AC and the limited case. So you can see in our core scenario, the AC framework saves $270 billion compared to the limited one. And that increases to almost $500 billion for multi-terminal. And this equates to a cost benefit ratio of, for our more aggressive transmission frameworks, 1.7 to 1.8. For AC, it's closer to 1.4 or 1.5. But you can see there's a big range. So in sensitivities where new low carbon technologies either weren't available or were more expensive, the benefit to cost ratios were even higher, closer to 2 or sometimes exceeding 2. And what's driving the savings across these different scenarios? The chart on the right shows different sources of savings for AC, point-to-point, and multi-terminal. And here we're talking about savings. So a positive number would mean these costs are lower than in our limited case, whereas a negative number would mean they're increasing. So if you look, for example, at the two blue colors, those are transmission expenditures. We're building more transmission in these alternative frameworks, so those costs are going up. But the biggest savings are from avoided generation and storage capital costs in green. These costs fall by 11% in the AC framework, up to 20% in multi-terminal. The second biggest source of savings is avoided fuel cost in gray. As we're able to add more transmission, we're able to build more low-cost renewables and generate more from renewables. And so fuel costs are declining by 44 to 49%. And I mentioned transmission costs are going up compared to our limited case. They increased by between 42% in the AC framework up to a 76% increase in transmission expenditures in multi-terminal. The majority of transmission expenditures are actually on spur line investments, which David mentioned. But we do see, especially after 2030, a big uptick in expenses on interregional transmission. And those reach about $20 billion per year by 2050. And then David talked about the high opportunity transmission or hot paths analysis. So we wanted to understand, what is the opportunity cost of not being able to build into some of these subregions? So we looked at just a couple of quick examples using MISO Central, MISO North, and SPP South, where we ran a couple of very high level sensitivities. The first being, what if we could build into these subregions, but we could only build half as much transfer capacity as our original kind of least cost optimal level? Or what if we could build into these subregions, but we're delayed by 5 years because we hit siting and permitting challenges or what have you? And then finally, as kind of an extreme bookend, what if we can't build any new transmission into these subregions? How is that going to impact at a system-wide level the value of transmission? So what we found was, and this chart shows the reduction in savings compared to our core scenario. If we don't allow any new transmission into these subregions, very extreme case, the total value to the whole system falls by between 5% in the AC framework to 20% and higher in point-to-point and multi-terminal. So some of these subregions have a very big impact on how much system-wide savings we could see from building more transmission. The good news is that if we have a 5-year delay in building the transmission, if we're not able to build as much as what would be optimal, we can still capture about 98% of those original savings, meaning that that first tranche of transmission that we're able to build into some of these high opportunity areas is extremely valuable. Now, the second question, who is benefiting from transmission? So we took all of those benefits that we had quantified, and then we regionally disaggregated them. Also, when regionally disaggregating, taking into account changes in purchase costs and generator revenue among regions using the adjusted production cost metric. And the chart in the middle shows the breakout. So now on the x-axis, we have the 11 transmission planning regions. And that black dot indicates the net of changes, both positive and negative. And there are some interesting kind of regional variations in terms of not just the magnitude of benefits, but the types of benefits that different regions are seeing. So for example, in SPP, with more accelerated transmission development between regions, SPP is building more renewables. They're generating more. So all of those costs are going up, but they're also able to capture more of the investment and production tax credit. And they're able to export power, and their generator revenues are also increasing. By contrast, if we look at a PJM, with more interregional transmission, they're building less generation, they're generating less, so those costs are decreasing. Their generator revenues are also decreasing, but they're able to import more lower cost power. And thinking about this in terms of absolute billions of dollars is one way to compare across regions. Another way shown in the map on the right is to look at the percent change in each region's total cost. So those numbers are too small to see, but a darker blue color means more savings. So if we look at on the east, New York ISO and ISO New England, they have in absolute billions of dollars, pretty modest savings, but as a share of their cost, they're saving 20%, sometimes higher under these alternative scenarios of their original cost in the limited framework. And then the future is very uncertain. So we also looked at the regional benefits under all of our different sensitivities that David described. And in some cases, it could range quite a bit. And the real drivers were the availability of different technology costs or different technologies as well as their cost. For regions that were building a lot of renewables, siting constraints on their ability to build had a big impact on the value of transmission for those regions, as well as some of our climate scenarios. Okay, and then the final question was, could we actually realize those benefits? If we were to build that portfolio of transmission today, would we see that $490 billion in savings? There are a lot of potential benefits that transmission can provide, some of them listed here on the left, but it's unclear if we could actually capture all of that value. So we started to look at how transmission was being used today, and we saw some symptoms, some indications that perhaps we wouldn't be able to really realize all of these benefits. Just as two examples, looking across 4 different seams on the upper right, we looked at how much during the year is power flowing from a high price area to a low price area, the hours of uneconomic power flows. And across these 4 seams, it was 40% or higher of the year. And in some cases, the price spread when this data was available was between $5 and $20 in orange, or even more than $20 a megawatt hour in blue. And we also looked at the utilization of transmission capacity between regions, which is very scarce already. So focusing just on ISO New England and New York ISO, This chart on the bottom shows different bins of price spreads between these two regions and the percentage of hours in the year where those price spreads exist. And the x-axis shows the amount of available but unused transfer capacity when those price differentials exist. So for example, if we just focus on the very bottom bar, in 4% of hours of the year, there was a price differential of $100 a megawatt hour between ISO New England and New York ISO. And on average, during all of those times, there was over 250 megawatts of available but unused transfer capacity. Now, there are a lot of technical and reliability reasons why some of these things may be occurring. But this might not be captured in some of our modeling results where we're showing big potential benefits of transmission. And it can also be the result of regulations or operating practices that aren't promoting efficient utilization of transmission. I'm quickly running out of time, so I'll go kind of quick here. So in the paper that's coming out in June, we dug deep into each of the regions, both market and non-market regions, to understand what are some of the barriers to using transmission, particularly interregional transmission efficiently, and what are some opportunities, specific opportunities tailored to each of those regions and their circumstances. And they're summarized at kind of a very high level here. In general, across all regions, whether there's a market or not, there are big opportunities to benefit from developing better frameworks to use resource transmission for resource adequacy. This either doesn't exist or it's designed in a way where you can't really use the transmission in this way in many regions. There's also a big opportunity for more joint planning so that system operators have the information they need to use transmission during extreme events and make sure that internal networks within a region can actually accommodate large transfers when those extreme events occur. And then out in both non-market and market areas, I think the general theme around a lot of the opportunities are around improved congestion management and improved scheduling, whether that's with firm bilateral contracts or in a market context where you have coordinated transaction scheduling. And then finally, we identified a number of more kind of national transformative actions that could be investigated more. Some of them came up in the last panel. So the first being more long-range national interregional transmission planning, whether that's led by a GDO or someone else, we can see what's appropriate. On the operational side, interconnection-wide intertie optimization to make better use of all of the resources in the interconnection. And then kind of a combination of those would be developing a new entity that could undertake the functions of planning and resource adequacy and scheduling. Now, all of these things are going to be difficult to do. These are complex issues. There are a lot of stakeholders with different interests. So we do not underestimate the challenge, but there are a lot of opportunities for improvement and a lot of excellent work already underway. So in summary, returning to kind of those initial three questions, what are the benefits of transmission from the NTP study? We found that accelerated deployment of transmission in our AC and point-to-point and multi-terminal frameworks could save hundreds of billions of dollars, primarily through reduced cost for generation and storage investments and operations. The marginal benefits of building that first bit of transmission to any of these important hubs are really high. In terms of who's benefiting, almost all regions saw benefits from more interregional transmission. It was quite sensitive and regions responded in different ways to uncertainty around technology cost and availability, as well as siting constraints and climate conditions. And can we get there from here? Do we actually have rules in place to allow us to capture some of these benefits? There are existing regulations and practices that could reduce the value of these investments if they were to take place today. But there are a number of both incremental and more transformative solutions that are being explored that could help improve this. Thank you.
Thanks, Amy. So I will go through some of the specific down translations now of those three scenarios that David was describing earlier. I might actually go stand over there so that we can look at the screen, but yeah, actually I'll do that. And as part of this exercise, we down translated three scenarios. When I say we, although that's my name there are a range of people at both of the labs, NREL as well as PNNL, that have contributed to this effort. You'll see necessarily why, as it is quite a complex process that we went through and established a set of workflows that, although the distinct solutions that you'll see here today are necessarily useful and potentially insightful, it's really about the workflows that then can be potentially utilized by industry in future, especially at a contiguous US or CONUS-wide scale. So the objective of this, without going into too much of the details, is to create these nodal data sets from the zonal capacity expansion outcomes, undertaking detailed operational modeling, utilizing production cost modeling tools, as well as power flow and then contingency analysis to inform the transmission expansion planning. You'll see what I mean by this in the next few slides, but really to take that translation from the zonal into the nodal world and start to really get an appreciation of the way in which these types of future scenarios would be operating. So some of those operational insights, but more specifically, because it's in the name as part of the NTP study or the National Transmission Planning Study, the types of transmission solutions that we're seeing across these three scenarios that we down selected. And what we do as part of that is not necessarily the sort of brown part that you're seeing there, which is the capacity expansion that's already been presented, but we take that scenario-specific optimal generation as well as transmission capacity expansion and disaggregate it down into this nodal world. So taking the generation, the new builds, as well as deactivations, the storage, as well as, of course, demand, and disaggregating it down into nodal. That's very prescriptive and very specific and scenario-specific in and of itself. The third step and the most important step is then this transmission expansion component, where we undertake an iterative transmission expansion planning exercise that is informed by or guided by the zonal capacity expansion in terms of interregional types of transfers and capacity that we're seeing. And the tools that we utilize as part of that is nodal production cost, linear power flow, and I'll start to show you that in the next few slides as well, but there's obviously potential next steps to do even more in that particular space. So this is exactly what I was mentioning now as we start off on the left-hand side. And as you move towards the right-hand side, we're increasingly representing or having a more refined treatment of nodal transmission needs or nodal transmission realities. And the reason that we went through the staged process is that you're perturbing starting point planning cases or nodal planning cases so substantially that it's really difficult to get towards feasible solutions, both in terms of nodal production cost, as well as then the power flow that follows that. So the first stage is we do this initial performance assessment where we use an unconstrained transmission representation. Some insights are gained there, but what we started to realize quite quickly is that the second step as part of that was then an interface constrained or transmission constrained nodal production cost, which starts to give us some information as to where the power is flowing, what's the average loading we're seeing on individual branches across these particular interfaces, those interregional transfer interfaces, and the congestion levels, the way in which the system's operating in terms of curtailment. We use that information in an iterative exercise as part of the stage 2 then. And within that stage 2, we go through a linear power flow or DC power flow. The reason that we introduce that as a step in between, so that teal box there, and then undertake the transmission expansion, is that we can really start to get quick turnaround. We don't have to wait for hours, potentially, as well as you'll see in some of the forthcoming slides, in the order of a day and a half at a time for nodal production cost model solutions, to then get quick insights as to transmission expansion, the feasibility or the impact of it in an interactive manner, rerun selected snapshots of which we choose intentionally to start to represent peak load, min load conditions as you classically are used to seeing, but also peak and min residual type of loading conditions, maximum transfers between big regions, as well as then transfers that are between non-adjacent regions. So for example, in the Eastern Interconnect between SPP MISO and then up and across into New York ISO or ISO New England. We then rerun the transmission constrained nodal production cost as we better representing transmission now and start to assess similar performance and the added value of the transmission that's been added. And we actually take the next step once we've got to a point that we are seeing transmission expansion feasibility, at least in this N-0 or system intact type of condition. We then take the next step as part of that stage 3, which is this iterative transmission expansion for selected contingencies. And without going into too much of the details, I don't think I'll have enough time today, but those selected contingencies are across each of the interregional transfer interfaces and one primary bus back from that. So we're representing contingencies on the main focal areas of the study, intentionally so. We're not going to be able to, and we weren't able to run contingencies for the entire US and assess the feasibility of a stage 3 type of solution, but at least between those interregional interfaces and one bus back from those, we're running contingency analysis, a DCE linearized contingency analysis to assess the feasibility of the expansion and see the expansion, the added value again, and running that final nodal production cost. I won't need to spend too much time on this because you've seen it, but this is just a quick summary of exactly what David was describing, those 3 scenarios from left to right, the limited, AC, and multi-terminal HVDC. The demand is the same across each of these scenarios in the order of 5,600 terawatt hours. In 2035, that's the model year, and there's a 90% reduction in that year in terms of CO2 emissions in the power sector. Again, the characterization being limited within each of the planning regions. AC expansion is allowed. AC expansion is allowed. AC is then expansion within each of the interconnects, so you're more free to expand the transmission. Then the HVDC multi-terminal is HVDC expansion across interconnects, as well as the same assumptions in terms of AC transmission expansion within each of the interconnects. And what that necessarily means is when you simplify it out to these 11 transmission planning regions and aggregate it up to at least the sub-regions that we've chosen, you can see the differential, of course, on the left-hand side, the limited, there's no transmission expanded, as you would expect, other than the small amount of prescribed capacity that are in the existing zonal capacity expansion models. The AC expansion by 2035, again, this is a differential relative to the starting point. You can see certain amounts of transfer capacity being increased across particular regions, in regions that you're probably aware of and that you would expect more transmission to be built as a result of more and more a changing resource mix by this particular model year. And then you see in the multi-terminal HVDC, that's a combination of total interface transfer capacity of the high voltage DC, as well as AC that's being built between each of those planning regions. The key difference here being the ability to expand seams crossing capacity, but at the same time, there is also interconnect HVDC expansion that happens. And I'll start to describe that in 1 or 2 slides a bit later. Nothing new here necessarily, just to mention that you're aware of where the large load centers are. The way in which we've then represented this and down translated the zonal capacity expansion outcomes into nodal models is utilizing these load participation factors that are in the planning cases that we've established, including, of course, conforming and non-conforming load details, but really then just distributing down that load into these particular nodes to then start to get an understanding of, if you start to have a very different resource mix, which I'll present in the next slide, you start to get an appreciation for the transmission needs that could then potentially meet that additional demand, both in terms of spatial changes as well as the temporal change, so the demand profiles and how those are changing in some of our demand forecasts. And this is what that looks like. So at the top, again, limited on the left, AC in the middle, and the multi-terminal on the right-hand side. The underlying transmission is not necessarily shown there, probably be too busy to see much. But what we're showing here are the points of injection at each of the nodes, down translated for each of these scenarios. The color codes you can see on the bottom right-hand side. The text is a little bit small, but the blue and the yellow are the solar and the wind. The remaining capacity in terms of other resources, nuclear, coal, natural gas, hydro, are also represented there. In a lot of cases, a bit smaller in certain regions and larger in other regions. But the summary at the bottom part of this is then across each of those planning regions and contiguous US-wide, the types of resource mixes that we are representing in these 3 particular scenarios. In the limited scenario, we have the least amount of transmission capacity in the order of 2,000 gigawatts. In the AC as well as multi-terminal HVDC, just under 2,500 gigawatts, of which that is dominated by a large amount of onshore wind and solar capacity. In the limited scenario, there's less wind and solar, as you would expect when you have limited ability to move really good resources from particular regions to load centers, but that is then supplemented by gas as well as coal CCS retrofits in that limited scenario. Now, I hope that this works. I'm not sure if it's going to, but what also came out of this was a visualization tool that we did call GridSight, but apparently there's something called GridSight already. So we had to rename it to something else. And so far we've creatively called it Gravy. I'm not sure if that's good or not. Seems like it's good. But what this really does is it enables us to do a few things. Number one, to do some level of a visual representation of these very detailed and very complex nodal models visually. So we can start to see where these resources are, as well as then over time, how they're being dispatched. And it looks like this is moving. But what we're representing here are nodal flows. You can see those flows and the directionality, as well as then the resources that are being operated on an hourly basis. A tool like this can be utilized really for anything, but for the purposes of what we were using it for is that data validation, as well as then for the purposes of aiding in our nodal transmission expansion planning. And then, of course, thirdly, the way in which different resources are dispatched, the way in which we're seeing curtailment in certain parts of the country can then start to really aid the way in which we expand the transmission on the basis of the particular down-translated scenarios. And what you're seeing here is just the AC scenario, 2 days in March. It's running now, it seems, which is great. And you can see the types of flows that you would see. Sun coming up, of course, solar being in some of the regions you would expect, in some cases. In other regions, that then obviously the sun goes down, the wind is still there, a lot of storage gets dispatched, but remaining gas as well as coal resources then dispatch up, and you start to see this hourly balancing and the types of insights you can get as a result of that. So those are those 2 days. We're in the middle of the second day now, but we don't have too much time, so I'm going to move along. So although there was a pretty picture, it's really useful to start to see that kind of information. But what I really wanted to show here is then the sort of snapshot information that we're getting out once we've post-processed some of this data, particularly here for the EI, the Eastern Interconnect, where you see the differential in the way in which the transmission network, before you start to expand transmission, you see where there's these key touch points where you need to be expanding transmission, as you would expect in an AC scenario, especially between regions, and where you would expect a lot of the power to be flowing. You need to be strengthening in those particular areas, potentially adding new transmission, new voltage overlays in particular cases where there's large amounts of transfers, or just potentially creating double circuits where there's single circuits, the potential for reconductoring and increasing ratings of existing lines. And just 2 points that I wanted to make here before moving on to some other interesting outcomes and some of the transmission solutions is the differential between the limited and AC scenarios is, of course, there's these larger unidirectional types of flows between regions that you would expect. So in that case, I know it's a little bit inverted if you can see the text there, but there's large amounts of power that's moving, in that case, between MISO Central and PJM East. In the AC expansion, it's about double that. So from the 10,000 to 20,000, 10,000 in the one direction and 20,000 megawatts in the other direction, to in the order of 30 gigawatts in the AC scenario. But an interesting outcome, and this is just an example between the Southeast and FRCC, so Florida is in the limited scenario, very much unidirectional types of flows that you see. But in the AC scenario, as you expand the transmission through that expanded transmission, you leverage the ability to transfer resources interregionally, and you have this bidirectional power flow between the Southeast and FRCC. And this is specifically shown here in this distribution, where you can see in terms of the distribution on the left-hand side, on the bottom left, not very interesting, pretty much always in one direction, other than in particular hours of the day. This is an average throughout the year, of course, the distribution throughout the year. And then on the right-hand side, the flow distribution, where you see this ability to move power back and forth. And in this particular case for FRCC in the Southeast, it's large amounts of solar that's then being exported out of Florida into the Southeast region. Although there's also a lot of solar in the Southeast, there's enough in Florida that's been built to then be exported out into the Southeast, utilizing that newly built AC transmission. And just going to spend one slide and then going to the transmission solutions, just in terms of models and model complexity and the problem characterization. You can read through some of the details, but when you combine EI, the Western Interconnector, and ERCOT, you have in the order of 95,000, 23,000, and 7,000 buses. The lines and transformers, generator and storage, as well as loads are shown there in summary. But in order to run these models at the different stages that I was describing, stage 1 and then stage 2 and stage 3, we do make particular assumptions for simplifications as part of stage 1. And these are summarized here, both in terms of the existing interface bounds, as well as in the new bounds that we add as a result of these scenarios, and the number of interfaces, the number of branches that are then being bounded. And then, of course, what that starts to do, if you look on the bottom part here in terms of solve time, is it really does increase that solve time quite substantively, even though we are breaking down the problem into 1 week at a time, 52 weeks being run in parallel with a horizon of 24 hours and an overlap of 48 hours. Of which one quick operational insight, and I've got about 5 minutes left, so should be sufficient, but just one quick set of operational insights: peak demand and minimum demand weeks, CONUS wide for the multi-terminal HVDC scenario. Some interesting insights here. Number one is that the period of peak demand, not so much curtailment as you would expect, because you have the ability to move power where it's needed across the entire country, not overstating the value of transmission, of course, but then in particular periods, for example, in the period of minimum demand, in the case of the peak demand, that was August. In the case of minimum demand, that's April. You see structural curtailment becomes a reality, where you do start to curtail lots of wind and solar, but these are economic outcomes from that capacity expansion zonal result, and you start to represent it nodally. You start to see this need, in this particular case, the stage 1 and the large amount of curtailment that we start to address as we expand the transmission, being guided by those zonal capacity expansion outcomes. And the interesting one on the right-hand side then is these flows between the interconnects that you wouldn't necessarily have today, is the seams crossing aggregated flows. In the top part here is between Texas and the Western interconnect, and then in the bottom part between the East and the West, where you have large amounts of, in the case of the top part, unidirectional flows, lots of solar and wind being built out in the multi-terminal HVDC scenario from ERCOT into WEC. And in the bottom part, you have this bidirectional flow back and forth between the Eastern and Western interconnect. In terms of orders of magnitude, in the order of 20,000 megawatts in either direction for the Eastern and Western interconnect, and then for the Texas and West, in the order of about 8,000 megawatts being transferred there in that particular case. So in terms of the nodal transmission expansion, just wanted to present some representative line locations and the nodal realizations of some of those transmission expansions that you were seeing. The existing transmission is shown in the back in gray. The additional transmission that's added to realize this particular example of the AC scenario is shown here. The red being 500 kV, green 345, and the blue being the 230 kV. There is a combination of strengthening or increased meshing of the existing network, but particularly in the AC transmission, you have this large amounts of interregional transfers and additional transmission strengthening, as well as new paths being created to enable that to happen. So for example, an introduction of 500 kV across into the southern parts of SPP, additional strengthening of the existing 500 in the southeast, as well as an ability to then move power between FRCC and the southeast. An extension of some kind of a backbone, at least for now, in terms of 500 kV up between MISO and SPP, as well as then that internal need to strengthen the existing 345 kV networks. In WEC, you also see a large amount of 500 kV. 345 wouldn't necessarily work because of the long distances. So these high surge impedance, long distance types of transfers are implemented in this case with 500 kV. You can see the combination of needing to strengthen on the borders of each of these scenarios for the offshore wind integration, which is consistent across most scenarios. And that's 500 kV in terms of the AC scenario that you're seeing here. In ERCOT, because of the distances being much shorter, we don't necessarily see the need for a voltage overlay to an additional voltage like 500 kV. So increased meshing of the existing 345 single circuits to double circuits, and then potential new pathways as part of that as well. And I've got 1 minute left, so I'm just going to run quickly through this. This is shown now, the HVDC multi-terminal scenario, but without the AC strengthening yet. This is work in progress, but the AC transmission strengthening that's happening is really indicative of, is shown in this next slide, and it's really indicative of the ability to expand HVDC is one thing, but the need to then pull those resources into the one side of an HVDC, whether it's point-to-point or a type of realization here, where you're starting to see this multi-terminal HVDC in 2035, is indicated in this map here, where you see the real need for Please keep in mind, this is intentionally showing where the AC strengthening is needed. So lots of overloads, but in the particular regions that you would expect. Where if I just go back and forth between these two quickly, you start to see that need to, you're moving power between the seams. You're also moving power north and south on the eastern interconnect. But the result of that is then this need for sufficient AC strengthening to actually enable that to happen on both sides of an HVDC terminal because of that bidirectional power transfer in some cases, or in other cases, a unidirectional transfer into particular load hubs. And that's it for now. I think I have run out of time, so Juliet's probably going to stop me. But here's some key takeaways. There's 9 of them here. I think I summarized them in each of the slides, but really just to say that we've taken these 3 scenarios. We've implemented a magnitude of HVDC expansion in the multi-terminal HVDC. We've implemented the AC as well as limited, but we're starting to see some really interesting insights in terms of the scale and the geographic dispersion of these new resources. The implementation in these nodal data sets is challenging, but it's possible, utilizing existing planning cases to do that. But some of these operational impacts that are also quite interesting, you'll start to see in some of the publications that are forthcoming later this year. So I'll stop there for now. I think that is the last slide, and I'll hand over to Nader.
Okay, as Nader's coming up here, I just want to remind everyone we are going to have some time for Q&A, so please jot down your questions, and there's going to be time for you to chat with the panelists at lunch and on break. So if you have a question that you think could help contribute to the national conversation, it'd be good for everybody to hear. We really want to welcome you to write that down and be ready to ask some questions at the end of Nader's presentation. So here you go, Nader.
Thank you. Okay, so good morning, everyone. So I will present another piece of the puzzle, which is the AC power flow analysis. So as what Jarrad just explained about PCM simulations, it's a full nodal realization of the new system with the additional generation transmission. But PCM simulation is limited. It will answer questions like how you do unit commitment, how you do economic dispatch. In such fully decarbonized system, it's more about how to optimize storage, how to minimize curtailment of wind and solar, how to avoid unserved load. It will show you the real power flow in the transmission network, the nodal transmission network, but it's based on a linearized DC power flow, which means voltages per unit at every substation, every bus. There's no reactive power modeled. So we need to move from PCM to power flow or AC power flow analysis to do more the typical reliability analysis that grid planner will do. So AC power flow models are typically used to comply with NERC requirements. You need, as you are moving from PCM to power flow, you need to do more careful planning of reactive power, like what additional reactive power devices you need to add to the system to guarantee voltage stability, how to make sure this huge amount of wind, solar storage added to the system are providing the same level of reactive support as conventional power plant. You want also to make sure when you have a contingency, either outage of these new lines or outage of big power plant, you still have enough reserve margin and your system still operate reliably under all N-1 and selected N-2. This is kind of the story of how we build our models. We started, the whole study, we started from well-vetted industry cases like for WEC. We started from, that was about 2 years ago when we started with WEC 2030 anchor data set. This data set has compatible power flow case, which means the topology in the power flow case has been the starting point to build the production cost model. So that this very compatible topology-wise. We started from these cases. We started our what we call high renewable baseline case. It's kind of optimistic business as usual scenario where we figure out, okay, without doing capacity expansion, just doing it more deterministic way, like all the project on the transmission project on the pipeline get built, and we are able to take advantage of building new wind and solar, taking advantage of this project and squeezing as much as we can wind and solar in the current network. And we came up with what we called high renewable baseline case, which will be like issued a separate report. And we're able to achieve about 73% decarbonization for this case. And we're able to run PCM at the nodal level and also power flow analysis to show this system still be reliable as the current system. After that, we switch it to our scenario work that the NREL team just explained. We add the capacity expansion model, to the original industry cases, develop nodal PCM, limited, inter-regional, and then the CONUS. In our case, we just developed the West and East, ERCOT is not included. And having these nodal PCM cases, we were able to extract power flow cases to do reliability analysis. For the East, we started from MMWG power flow case for year 2031 that the whole study used with input from EIPC or Eastern Interconnection Planning Committee. And then we built the PCM model on top of that, both NREL and PNNL teams. So I will just give you a kind of few scenarios for the work we have been doing and how we did the EC power flow analysis. This realization is based on round one of the capacity expansion modeling, which happened in earlier stage of the study. So for WEC, we have two different scenarios, as Jarrad mentioned before, inter-regional versus limited. In round one, the main difference between these two scenarios, and inter-regional, you have more wind, you have more transmission, versus limited, where you have more solar, more storage. And it was kind of in play between the Rocky Mountains and the Desert South, like more in the inter-regional, you have more wind in the Rocky Mountains, versus maybe in the limited, you have more solar in the Desert West. This is the nodal realization, like this is the transmission build in each scenario. After like we ran fully modeled in PCM in both cases, you have 8760. And now we want to select some certain hours of interest and run our AC power flow analysis to see how reliable this grid and compared to our current grid, it's the same level of reliability. These are imaginary scenario, or it can happen in the future and can still operate reliably as our current grid is. So to do this conversion or moving from PCM to power flow, we are using a tool we developed at PNNL. We have been using it for a few years now called Chronological AC Power Flow Automated Generation Tool, or CPAGE, which basically connect between PCM simulation and original power flow case, and take the dispatch of generation unit, load, storage, dispatch, everything coming from PCM, it will import it to a snapshot. AC power flow is just one single snapshot for certain hour. And after certain iteration, trying to get the reactive power correctly, you get converged AC power flow using commercial tools like PSSC, PowerWorld, or PSLF. One typical question we get, should we do all the 8760 hour of production cost modeling for 1 year to run AC power flow analysis? Most probably the answer is no, you don't need to do 8760, but you can do some intelligent sampling based on which generation mix online, wind, solar, load, time of the day, season of the year, load value, and so on. So typically we found about 2.5% sample is sufficient, which means about 200 hours out of the 8760 could be sufficient. Also, you could put all this data into a database and query the database. Like I'm interested to get an AC power flow case where this new line is 80% loaded and the load in the network was 90 percentile. So what's the impact of this new line, highly loaded outage on the system? So you can simply query the database and come up with a power flow case to answer your question. So the process, we start first, make sure, extract DC power flow cases from PCM, make sure the topology is matching by comparing flows for certain days for chronologically for 24 hours, and make sure what we see in the PCM is similar to what we see in the DC power flow. The next process is converting from DC to AC. You have to consider losses. So we have to play with generation load to account for losses. And the last piece is to get the conversions by do like QV analysis or reactive power voltage analysis to make sure we're adding additional device. So we get a nice converged case that could be the starting point for additional contingency analysis. For contingency analysis, we are not running full-blown planning contingency analysis, but we are just trying to show how robust this future system could be as the current systems. So we are checking few N-1, N-2, and in our case, we select for WEC some backbone lines, 500 kV and above. We also concentrate on the new addition or these new added lines and circuits, make sure these new lines are not representing high risk on the system. And then the typical governor or could be pseudo governor response. If you take like one big unit out of service, do I have enough reserve margin, enough units online to cover these units? So I'll give you a few examples, and this is a typical contingency analysis. When you have contingency, you relax your voltage by about 5% voltage limit, and also you allow additional flow up to 35% beyond rate A. That was our assumptions. So I'll give you a few examples on how we do like this kind of contingency analysis and sample cases from the production cost model. So this is one example in the inter-regional case. We're interested in one of those new lines that we have built, this particular line where you have the rectangular, red rectangular. It's moving wind from New Mexico, central New Mexico to the southwest part of it. And it's a double circuit each at this particular hour, which we are interested in here. It was August 2nd at 10 p.m. The line, each circuit was loaded about 1500 megawatts. So when you have a double circuit outage, we're talking about 3000 megawatt outage. It's very large contingency. And this is the generation mix at this hour. So it's mountain time, it's no summer saving. So that's summer saving would be like around 11 p.m. So you can see the main generation at this particular hour, 27% coming from natural gas, 25% from wind, 17% from storage, PS storage, and then 16% from hydro. These are four main generation mix supporting the grid at this time. The load is 163 gigawatt. So we take these two lines out and see what will happen in the system. So this is before contingency. This is and the one on the left, the one on the right after contingency. What happened as you'd expect, the flows as coming to parallel lines to this line that we took out. These lines are still within acceptable limit under contingency. So that will tell us, yes, we still have a sound design with this new transmission. So this new transmission is not representing high risk to the system. We can also take the result more to do additional visuals, like we have a database where we can import all the power flow solution into our database. And then we can start to see, this is like a voltage heat map. So green means you are still within the acceptable limit. You can also see the flow in this map. So you can see on the left side or the right side, you can see the big arrows here, which it's the yellow ones around the area of contingency, but still within acceptable limit. You'll see higher flows in the surrounding line, but still overall, the system is in acceptable stage. You can do, again, your typical contingency analysis. You can dig into Excel files with all the values and examine further, but visual will give you a quick insight on what's happening on the system before and after contingency. I'll take another example. This is for the limited AC case. And this is, again, the same day, August 2nd, but this is 4 p.m. And as you can see, like the majority of the load at this particular hour, as you'd expect, supplied by solar, 55% supplied by solar. And you can see the flow in the line during the day is really impacted. It's shaped by solar, like it's going dipping down at noon and then going up back, ramping up back. So the hour of interest here was hour 16 or 4 p.m. This again, new line. It's connecting between New Mexico and Arizona. And in our design, that was triple circuit. Each circuit was carrying about 1,000 megawatt. So we take two circuits out of the three circuits as a contingency, about 2,000 megawatt contingency. And same story, on the left side, this is before contingency, on the right side after contingency. And you can see the remaining circuit is overloaded, but still within acceptable limit out of the three circuits. And then the flows are at the AC network going to the neighboring lines, still within the limit. So again, it's realizing that such a future system can still work reliably, and these lines may not show like a high risk to the system. Same way, we can also visually inspect before and after contingency in terms of voltage profiles and flows, and make sure the grid is still in acceptable status. Another example is governor response. Like we would like to see, if I lose big unit, like in our case here, like a typical wake contingency double Bellevue units, which about 3,200 megawatt, if I recall correctly, or 2,600 megawatt. And here we are comparing between three different cases. One is the original industry wake case, where the load at this particular hour at 8 a.m. in July 21st, the load is 110 gigawatt, versus our scenarios where we assume significant increase in load. So our load, because of electrification, the load is higher, about 155 gigawatt, and comparing these three scenarios. One interesting thing here, you can see in the original industry system, solar supplying 16% of the load. In the other cases, solar is playing much larger role, 44%, 48%. Natural gas still playing a role, but less compared to the original case. And this is a comparison between how, if you take these 2 units out, what units in the system will respond and covers or provide the kind of pseudo-governor response. So in our case, we don't allow wind and solar because we don't curtail them, so we don't have headroom to provide such service. So it will be mainly transition. You can see in the original system, it was mainly hydro and natural gas providing the governor response. In this new system, it will be mainly storage. Actually, what's happening here, even though you don't see storage in the mix here, but storage is actually acting as a load, like you are charging storage at this point. So when you have loss of generation, what will happen simply, you allow storage load to be decreased significantly, so you recover the loss of generation. So rather than changing generation, you simply, storage will take a role of reducing or load reduction, so you don't need to play like other generation to respond. So we see that in this kind of big, large unit outage, storage will play more key roles in the future to provide such service. Okay, I will go through the remaining slide just about Eastern interconnection. That's much more complicated, but I will, and then going all the way to the CONUS case. So to develop a CONUS case that has East and West, we have to start stitching the PCM models in both East and West and make them one single model, including the back-to-back ties. We convert that to short HVDC lines. And also need to do the same in the power flow, like stitch the power flow case with East and West together and make sure you get a nice converged power flow case. So we started with the East. After we built the production cost modeling in the East, we compare export DC power flow case, compare the flow from PCM versus DC power flow. We look to the magnitude and shape. They are identical. These are 2 examples. So that tell us topology is the same in production cost modeling and power flow. So we can move to the next stage. We'd like to get one particular converged power flow case as a starting point for the Eastern interconnection. So you select certain hour here. I think that was August 10th, 6 p.m., something like that, or 4 p.m. or 5 p.m. And go through the exercise of conversions. And we had some issues. The Canadian part, you can see the red here. We are working fixing that, some few violation here and there. But overall, we're able to get a nice converged case to some extent that we are keep improving, working and making it in a better shape. And then once we get the Eastern interconnection case, we stitch it with the Western interconnection cases that I showed later. So without going into detail, these are the one above is the West load shape at this particular day. The one in the middle is the East, and then when you stitch them together, that's the whole system load. And these are the generation mix for each one. WEC, East, and CONUS together. And then we end up extracting power flow case. Now we have one fully functional, like we use PSSE for this case. This is a full CONUS case with converged case. It still has some voltage violation. As you can see, these red and blues are not within the limits, but it's converged, and we are working to keep improving it until almost there. I didn't, by the time I prepared the slides, we have some more promising results that we have a nice converged CONUS case that we called it our starting point or ground zero for the capacity expansion work. And so now what we are working on now is the multi-terminal HVDC that Jarrad mentioned. In our case, we completed this work on the production cost modeling phase. It has about 85 sections. Each section has about 1 to 4 circuits, a total about 100 bipolar in multi-terminal HVDC. And we were able to get 8760 in the production cost modeling, and now we are trying to get few hours and to get easy converged power flow case for this scenario. Now, the challenge we found with the MTDC, the industry or commercial tool are still behind in modeling this correctly. Like even in production cost model, we had to work with Hitachi to improve the grid view model to be able to model multi-terminal HVDC mesh network correctly and get the result that is realistic. And now when you move to AC power flow, we found that, again, commercial tools are still behind. You can model 1 or 2 lines separate from each other, but you can't really model a full-blown meshed MTDC and commercial power flow tools. What we found, like there is an approach in some literature in the IEEE we have been using where you split the AC and DC network. So we are modeling all the equation for the DC network in Python and having boundary condition between the AC and DC until we get convergence. So we have other projects that examine this approach successfully, and we are trying to leverage the same approach. So that's work in progress until we get a nice convergent case. But it's not as easy as, because you have to do this kind of co-simulation between two different platforms. But there's preliminary promising result for that. And once we have this case or power flow cases for Zakonas, we will concentrate on the themes like what if there's about 20 gigawatt connection between East and West that we are going to examine what if any outage between East and West, how that impacts grid reliability. Also, most of MTDC are large lines, 4,000 megawatts. So we would like to see if you get like circuit outage, are you still survive with such large outage or not? That would be our next investigation. So again, the takeaway, I'd say three major points. The future really is linking between PCM and power flow. Like maybe gone are the days when you try to develop power flow case manually, high load summer case, high winter summer case, low load spring case. That maybe will not work to realize or to examine future scenarios. We need to have seamless transition between PCM and power flow to examine these future scenarios. The future scenarios, even though it has significant amount of wind, solar storage, IPR, it could be as reliable as the current grid. It can withstand large contingencies as we see in our current system. Additional full-blown planning analysis needs to be done, but these preliminary results show it could be as reliable as current system. Last point is the analytic. You have a lot of data coming from contingency, from PCM. You need really to put all of that in one single database and do more visuals, more data analytics, query, and so on. So that's really important with this new system to better understand their behavior. And thank you. That was my last slide. Just in time.